Okay, we're going to talk about gas laws. But to talk about gas laws, we've got to introduce a few concepts first, okay? And we have to talk about some units. Because remember, we have a calculation, our units are important, okay? So we're going to start off talking about pressure, volume, and temperature. Pressure is the force exerted over an area. Okay, the force exerted over an area. So we have what we refer to as atmospheric pressure. Atmospheric pressure is really nothing more than the weight of the atmosphere. At sea level, a column of air, 1 square inch, so 1 inch by 1 inch from sea level to the top of the atmosphere, weighs 14.7 pounds. So 1 atmosphere, 1 ATM, is equal to 14.7 psi. So if you're down at the beach, every square inch of your body is supporting 14.7 pounds of air from where you are to the top of the atmosphere. Okay? Well, this is an English unit. We need to have a metric unit. So, in terms of a metric unit, 1 atmosphere of pressure is equal to 101,325 pascals, which is a Newton per square meter. Okay? You may see it as 101.325 kilopascals. So that's the unit of pressure. And that's equal to 1 atmosphere. And all of our pressures that we calculate are going to be in reference to that 1 atmosphere of pressure. Now, in other units, this is also equal to 760 millimeters of mercury. So if we have a column of air and a column of mercury, the same dimensions, the air column from sea level to the top of the atmosphere is going to be equal to the weight of a column of air of the same dimensions, 760 millimeters high, or 76 centimeters high. Now, when you watch the weather, they give you atmospheric pressure. They generally give it to you in terms of an inch, or inches. It's somewhere around 29.5 to 30.5 inches. Okay, when pressure increases, the weather is good, and when pressure decreases, the weather turns sour and possibly begins to rain. Okay, so those are English units. We're going to be using the metric units here for pressure. Now, that's atmospheric pressure. We have 2 types of pressure. We have absolute pressure, and we have gauge pressure. Gauge pressure is measured by a gauge. Okay? And in reality, it's the pressure above atmospheric pressure. If your car tire is flat, what's the pressure in your car tire? 0, according to a gauge, right? Agree? The pressure inside the tire is actually equal to the pressure outside the tire. A gauge measures a difference in pressure. So the gauge pressure would be that above atmospheric pressure. So if you've got 35 psi in your car tire, that means it's 35 pounds per square inch above atmospheric pressure. Okay? Absolute pressure is the sum of the gauge pressure and the atmospheric pressure. So if your tire's flat, the absolute pressure is atmospheric pressure. 14.7 psi if you're at sea level. If your car tire's aired up and it's got 35 psi of gauge pressure, the absolute pressure would be 35 psi plus 14.7 psi, which would be around 50 psi absolute pressure. So you've got to look at it in terms of the two types of pressure, okay? Now, volume. Generally with gases, we use the liter for volume, okay? When we talk about solids or liquids, we talk about densities in terms of grams per milliliter or grams per cubic centimeter. When we talk about air, or any other gases, we generally talk about masses and densities in terms of grams per liter, because air is not as dense as a solid or a liquid. Also, when we look at temperature, we have to look at something called the Kelvin scale, or the absolute scale. Okay, and remember, to get Kelvin temperature, Kelvin is equal to degrees Celsius plus 273.15. So all temperatures must be in Kelvin. We generally are going to use the liter 99.9% of the time. And our pressure is dependent on what units that we're using in the problem. Okay? So we have 5 different relationships. We have 5 different relationships that we're going to talk about. Okay? And they all fit in specific areas. Okay? The first is a pressure-volume relationship, and it's referred to as Boyle's law. Boyle's law states that there's an inverse relationship with pressure and volume. There's an inverse relationship between pressure and volume. So if I increase the pressure on an object, the volume decreases. Now that's hard to comprehend sometimes when you think about a balloon. To blow the balloon up, you increase the pressure, right? But that's the internal pressure of the balloon. When I'm referring to the pressure, I'm referring to the external pressure of the balloon. So if I've already got my balloon full, and I increase the pressure on it, the size of the balloon is going to decrease. In other words, if I tie it to a brick and drop it in the water, the brick's heavier than the buoyant force of the balloon goes down, 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 down. The size of the balloon is going to decrease, 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 decrease. If I cut the string, the balloon comes up, the size is going to increase, 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 increase. Okay? So it's an indirect relationship, or an inverse relationship. P1 V1 is equal to P2 V2. In this relationship, called Boyle's law, the temperature must be constant. So the temperature cannot change. The temperature cannot change. It must be a direct relationship. It must be a constant temperature, but an indirect relationship between pressure and volume. So that's the first gas law. The second gas law is Charles' law. Charles' law is a direct relationship. It's a relationship between volume and temperature. If I increase the temperature on an object, it increases its volume. If I decrease the temperature, I decrease its volume. For instance, if I go buy balloons in the wintertime, helium balloons, I buy them in a store, they fill them up with helium, the store is warmer than it is outside. I walk outside with my helium balloons seem to deflate. I get them home, I take them out of the cold car, put them in the warm house, the balloons inflate. Okay? So it's a direct relationship. Here with Charles' law, the pressure is constant. So I've got 2 laws here. One holds temperature constant and one holds pressure constant. How many situations are available where we can hold temperature constant or pressure constant? Not very many. So what we want to do is combine these 2 laws, Boyle's law and Charles' law, and we've come up with something called the combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. We don't have to worry about anything remaining constant. Everything can change. In other words, we have 6 variables in this equation where we only have 4 here and 4 here. So if we're looking at a problem and the only information in our problem that we have is pressure and volume, we can only use Boyle's law. If we're working at a problem and the only thing we have available in there as far as variables go is volume and temperature, we can only use Charles' law. Cannot use Boyle's law. See how we're forced to use this. If we have pressure, volume, and temperature, we can use this law, and we can't use either of these two. So the number of variables that we have in our equation, or in our problem, dictates which equation that we're going to use to solve our problem. Okay, we got 2 more. One is called Avogadro's law. And Avogadro's law is really nothing more than a statement. It states that 1 mole of an ideal gas at STP, which is standard temperature and pressure, is equal to 22.4 liters. 1 mole of an ideal gas at STP is 22.4 liters. Now, we've got to define STP. STP is 0 degrees Celsius and 1 atmosphere of pressure. Now remember, we can't use Celsius as our temperature, so what temperature are we really at? We're really at 273.15 Kelvin and 1 atmosphere of pressure. Kind of a trick question there when we're looking at it. Now, if I have 2 moles of an ideal gas, it would have a volume of 44.8 liters. If I have half a mole of ideal gas, it would have a volume of 11.2 liters, right? Okay? Now, what's an ideal gas? Well, it's a gas that acts ideally. Or, we can look at it in terms of a real gas. An ideal gas is a real gas that's not experiencing a phase change. In other words, it's not going to be converted to a solid or a liquid or a plasma. When does that occur? Well, it depends on what the gas is. But to have an ideal gas, it must not be at high temperature or high pressure, or low temperature or low pressure. So that's important to know. That's really, really, really important to know. When does a gas not act ideally? When it's at high temperature, high pressure, low temperature, or low pressure. Or in other words, when it's ready to have a phase change. For all practical purposes, our gases, our normal gases, our real gases, all act as ideal gases except when they're having a phase change. Okay? And we got 1 more gas law, and it's called the ideal gas law. The ideal gas law is PV is equal to nRT. Now, N is the number of moles. Okay? Which comes from Avogadro's law. Remember, one mole of an ideal gas at standard temperature and pressure has a certain volume. Okay, so there's a mole to pressure volume relationship. R is the gas law constant. Okay? R is always equal to, in Chem 1 when we're working gas law questions, 0.08206 liters atmospheres per mole Kelvin. So you've got 4 variables there, PV, N, and T. Pressure, volume, the number of moles, and temperature would give you the ideal gas law to use. R is always going to have that value when we're working problems in Chem 1. Now in Chem 2, when you get into talking about energy, R is going to have a different value, different set of constants, different set of units. Okay, so in review here, just a simple quick review. If I've got a problem that has the variables of PV and PV, I use Boyle's law. If I've got a problem that uses volume and temperature, I just use Charles' law. If I've got all six, pressure and volume and temperature, I'm looking for the combined gas law. If I've only got PV and N and T, I use the ideal gas equation. And if I'm looking at terms of how much volume, moles of gas used, I use Avogadro's law. Now, if I give you grams of gas, what do I have to do to that? I have to convert it to moles because my relationship is not grams of ideal gas at STP, it is moles of gas at STP. Okay, so you've got your 5 gas laws, and you've got these 3 things that you have to be mindful of. Okay, that your pressure has different units, your volume needs to be in liters, and your temperature must always be in Kelvin. Okay, now, you can ask questions. Do you have any questions on anything? And the next time we come to class, we'll work problems just with those equations. What I'm going to do is I'm simply going to write those 5 equations on the side of the board, and we'll pick a problem and work it using one of those 5 equations.